Right. Great. So today we have Simone Giacomelli take a journey with us through Argyres Douglas theories. Take it away.
Okay, thank you very much for the invitation. So in this seminar, I will try to give an overview of recent results about this class of n=2 theories in 4 dimensions, including some of my own results in collaboration with many people who are listed here. So I start by acknowledging them. Okay, we will discuss, as I said, Argyres Douglas theories. So we will start by reviewing basics of for the n=2 theories. And then I will discuss the main methods we have to construct them essentially by embedding them in string theory, classes, and type 2B compactifications. And then I will discuss some methods we have to study these models, their properties, in particular the spectrum and moduli space. I choose to review methods based on quivers, so BPS quivers for the spectrum and magnetic quivers for the study of the X branch. There are also other ways to approach these models, for instance, using spectral networks or chiral algebras, which I will not cover due to lack of time. So let's start by reviewing the modular space of n=2 theories. So all such models have a space of vacuum, the modular space. In the case of CFTs, all these theories have a canonical U1 times SU2 global symmetry from the superconformal algebra. And we have 2 distinguished branches on which part of this global symmetry is preserved. In the case of Lagrangian theories, the X branch is classically exact, not subject to quantum corrections. This is not the case for the Coulomb branch, which is instead quantum corrected. And we know exactly how, thanks to the Seller-Witten solution, we can fully take into account quantum corrections. Okay, so the usual thing we do to characterize n=2 theories, even in the absence of a Lagrangian description, is to focus on the Coulomb branch and describe its properties. In particular, in the case of CFTs, we look at the spectrum of operators on the Coulomb. Okay. Now, what do we mean by Argyres Douglas theories? Well, usually we mean models with Coulomb branch operators of fractional dimension. This property automatically rules out a Lagrangian description. These models are always strongly coupled. Typically, they involve on the abelian vector multiplets, which interact with electrons and monopoles at the same time. So we don't have a weak coupling description for this. They are also different from gauge theories as long as degrees of freedom are conferred. In particular, the central charge A is usually considered the way to measure the number of degrees of freedom, scales linearly with n for large n, instead of quadratically as for standard gauge theories. Here, by large n, I mean the dimension of the Coulomb branch. In the case of Lagrangian theory, it coincides with the usual notion. So since these models don't have a Lagrangian description, we can ask how we can study their properties, for instance, the spectrum or the X-branch, since so far we have discussed the Coulomb branch only. And we will see how we can try to answer this question. So let's see, first of all, how these theories were originally discovered. This makes use of the Seiberg-Witten solution. I will mention the Seiberg-Witten curve in passing a couple of times. It's not essential to know exactly what it is. So the first result concerns the SU3 super-Yang theory. This is a known Seiberg-Witten curve, which is written here. The Seiberg-Witten differential, which is used to compute the mass of BPS states, as this expression, where we have the derivative of the polynomial appearing in the curve. So the idea, anyway, is to start from an asymptotically free theory. So we have a mass scale. This lambda is the dynamical mass scale. U2 and U3 describe the expectation value of Coulomb branch operators. Here we have 2, since the rank of SU3 is 2. And the idea is try to locate points on the Coulomb branch where the curve degenerates and becomes singular. In particular, as you can check, for these values of U2 and U3, 3 of the roots collide and the curve becomes singular. If we expand it around one of these singular points, we get an expression of this type. So the curve becomes elliptic, and the expression for the Seiberg-Witten differential also simplifies. Now, since we don't have the scale lambda anymore, this theorem might describe a superconformal point. The scaling behavior of curve and differential are compatible with this interpretation. How do we determine the spectrum of operators? Well, since the Seiberg-Witten differential measures the mass of BPS states, we set its scaling dimension to be 1. Okay, that's the normalization condition. And then, requiring homogeneity of the curve, we end up concluding that this new parameter U3, which is simply the fluctuation of U2 and U3 around this point, has dimension 6/5. So here we see fractional scaling dimensions appearing. Okay, this was the first example. Of course, we can play exactly the same game for any gauge group. Here we chose SU3. We can pick any super-Yang theory, and we end up with a different AD theory for any choice of simply laced group. If we choose G to be non-simply laced, we don't get new models. We still get the simply laced ones. This was discussed in this paper by Eguchi and Hall. We will call these models A1, G. I will explain later this notation. As long as I know, this type of analysis has been performed systematically only for theories with a simple gauge group. So either super-Yang or QCD with matter fields in the fundamental representation. In principle, we can do the same for more complicated theories. We can start, for example, from Quiver theories or more exotic matter representations. But usually what happens is that the algebraic complexity of the curve makes it hard to make a systematic analysis of singular points in the Coulomb branch. So we may need more efficient tools to construct more examples of these strongly coupled theories. And that's what we are going to discuss next. So The first one I would like to discuss is classes. As is well known, this is a good and efficient way to build a large class of theories. Most of them are not Lagrangian, they are strongly coupled. We can describe classes models using an itching field which lives on the Riemann surface on which we compactify the 2,0 theory. A key ingredient of this construction is the presence of punctures. So the itching field will be singular at the punctures on the Riemann surface. When the pole is simple, the puncture is called regular, otherwise we call it irregular. A key point is that we can construct many models of this type with fractional scaling dimensions. If we consider classes theories with irregular punctures, we should do that. We can also get a few just by using regular punctures in the presence of twistings, but this gives a very limited set of examples. So we focus on this class of irregular punctures. So at an irregular puncture, the itching field has this behavior where generically this parameter R is larger than 0. And we have this sort of block decompositions where these AI are semi-simple matrices. Okay. These have been discussed quite in detail in these two papers, and recently we gave some more examples of irregular punctures in this reference. Okay, one thing which is not so trivial to see is that if we want to describe superconformal theories with irregular punctures, we have to take as a Riemann, we have to choose the sphere as our Riemann surface. We can include only one irregular puncture, and if we want, we can add on top a regular one, just one. If we have more punctures or a Riemann surface with a different topology, we always end up with models which are not conformal. They are either asymptotically free or infrared free, as was discussed in detail in these two references. So we can play with spheres and two punctures on them. Okay, so let's just have a look at some examples. We can focus on 2,0 theories of type SUN, which is the simplest case. And we have essentially two classes of theories we can consider. So one feature of classes models is that from the itching field we can easily write down the Cyber-Witten curve. It corresponds just to the characteristic polynomial of phi. Okay, and this is what I will use to describe the resulting theories. So if we have just one irregular puncture on the sphere, we can consider the case in which we have only one block with a pole of higher order. In this case, we get Cyber-Witten curves of this type. If we set k equals to 2, we land on A1, SUN theories. And just by changing the type of 2,0 theories, we recover all the A1, G models I discussed before. So we see those are just a special case of this construction. And then we can also consider the case in which the itching field has more than one block. In particular, we can consider two, one irregular and the other one is irregular with R equals 0. In this way, we can introduce monobilian global symmetry. In this case, since G is SUN, the resulting models will have unitary global symmetry. A is the size of the regular block, and we have a Seiberg-Witten curve of this one. Now we can refine this construction by adding regular punctures, changing the type of 2,0 theories, or we can also include twisting. So we can have twisted punctures, meaning that as we loop around the puncture, the Hitching field undergoes a transformation given by the outer automorphism twist of the AD algebra underlying the 2,0 theory. In this case, we also need a regular puncture because the twist line looks like a cut on the Riemann surface, which has to start and end somewhere. So I need at least 2 special points. Okay.
What is the order of the pole in those cases for the irregular? What is the value of R?
So in this case, R is 1 plus K over N.
Mm-hmm.
Okay, so
the pole is of order slightly more than 2.
So the order of the pole is 2 plus a rational number which can be which can be less than 1. In principle, we can have R smaller than 1, but it turns out that in this case, we are forced to introduce a regular puncture as well. The regular puncture cannot live in isolation, but it exists. That's something we can do. Okay. This is one way to construct Argyres Douglas models, which generalizes the cases we have considered before. We don't have a description in terms of embedding inside the Lagrangian theories in general. These are way more complicated. So with this method, we can go beyond your original approach. Now, I would like to describe a second method, a second tool we have to construct these theories, which is compactification of type 2 strings on a singular favifol. We take a singular Calabi-Yau so that we can decouple gravity, and we are left with a field here. Why type 2b and not type 2a? Well, we can also study type 2a. However, the nice feature of the type 2b setup is that complex structure deformation, so classical geometric notions, provide us with the exact Seiberg-Witten solution, including quantum corrections. And then if we want to study models without a Lagrangian description, this setup is better because it gives an easier handle on the theory. At least we can read off directly the properties of the Coulomb range. Let's consider again some examples of this. So the simplest class we can consider is that of hypersurface singularities in C4. So we have a single equation in 4 variables. One special class, which is discussed in detail in this paper, is given by this type of F, which is the sum of 2 AD singularities, both G and G prime are of type AD. And we call these models GG prime Argyres Douglas theories. And here we see the reason for the notation we chose at the beginning. All these models can uniformly be described in this way, with an hypersurface singularity. So the case we discussed at the beginning is given by G equal A1, SU2. Then we can also describe Lagrangian theories with this method. In this case, we have to consider a slightly different class of singularities of this type. So again, we have an AD singularity, and then we have this exponential dependence on one of the correlates. This gives G super Young-Mills. Of course, we can trade X for its log. We can take we can work in terms of Z instead of the exponential of X4. In this way, we end up working with hypersurfaces in C3 times C star. This can be generalized again using this C star variable by changing the exponential. The interpretation of this equation is again a G vector multiplet coupled this time to a strongly coupled sectors, which we call DPG. So when we turn off the gauge coupling, which formally at the level of the geometry corresponds to dropping this term, Z to the -1, we get these theories with non-abelian global symmetry, which can be AD. There is no restriction. Okay, so now,
what are the restrictions on P in the last example?
There are no restriction on G, and there are no restriction on P either. Of course, if we pick P equal 1, we go back to the case number in which we have only super Young-Mills, which means that the SCFT in this case is trivial, is empty. Okay. D1 is trivial. The other models are not.
But you say otherwise no restriction on P.
No. Can be generic. And by the way, going back to your previous question, if P is less than the dual Coxeter number of G, we have examples of these irregular punctures with pole order less than 2. Okay. This also has a class description. Okay, so we have this nice method to construct strongly coupled theories, but indeed we cannot pick any random F. There are some constraints. So if we want a conformal theory, we should take a homogeneous hypersurface. This reflects the Hessian invariance of the theory. And we require the singularity to be isolated. So there is only one point, the origin satisfying this constraint. This ensures we have a 4-dimensional theory. And then there is a more complicated one, which is the following. So since we are considering string theory on a Calabi-Yau space, on the worksheet of the string, we have a 2-dimensional theory, which includes a Landau-Ginzburg model as a subsector. The defining equation of the hypersurface in this context is the superpotential of the 2-dimensional theory. So I treated the 4 variables as chiral multiplets. And the central charge of this 2-dimensional theory should be less than 2. This condition implies that the singularity is at finite distance in the modular space, as was discussed in these two references. So let's see why the second condition is important. So let's consider, for example, this F, just the sum of 4 cubes. This is just a rewriting of the G4 theory. So okay, it's indeed ACFT. So as in the case of the Seiberg-Witten curve, we can determine the spectrum of Coulomb branch operators. And in order to do this, we have to assign scaling dimensions to the various coordinates. In this case, the normalization condition is given on the holomorphic Favy form, since again its periods on Favy cycles gives the mass of BPS states. And for this reason, we impose the same normalization. The scaling dimension of omega should be equal to 1. Okay. In this case, if we do it, it's easy to see that the normalization condition tells us that all the 4 coordinates have dimension 1. Okay. Now let's try to do the same for this F. So we replace the cubes with 4 powers. Omega has always the same structure, and now we see that numerator and denominator have exactly the same dimension. So no matter what the assignment of dimension of xi is, omega always ends up having dimension 0, which means that we cannot impose the normalization condition. And this is telling us that this is not an actual CFT. What does not work in this case is precisely the second condition. In this case, the central charge is exactly equal to 2. And here we see that it's important to require the strict inequality. Equal to 2 is not fine. One can easily check that being able to impose the normalization condition is equivalent to requiring the second. Okay, so these are the basic restrictions. Apart from this, we can pick any F, and this can generate a large class of CFTs. Okay, now I would like to briefly compare a bit these two methods. So class S and geometric engineering. So at first sight, one might think that geometric engineering is more general, because the case of irregular punctures with a single block, which we described at the beginning, just provided this set of models. They are of GG prime type, where one of the 2G is SU. Okay. Adding a regular full puncture to the setup just leads to DPG, which again fit in type 2B. And it's less trivial to see, but one can actually check that also including twisted irregular puncture leads to models which can be described as hypersurface singularities. So we may think that type 2B covers more than class S. On the other hand, from the class S description, just by choosing a different regular puncture, not just the full one, is other type of models which do not have the type 2B description. And also, and the same thing applies to the case with two blocks. Before we said that from class S, we can have two blocks. One of them is regular. This allows us to construct models with a non-trivial global symmetry. We have seen that the Sabel-Witten curve has this form. And this, morally speaking, would correspond to hypersurface singularities F of this form. However, we can easily check that for a larger than 1, these are not isolated. So the geometric engineering setup does not apply. So I would say both techniques provide us with a very large class of models. They have a sizable overlap, but they are not contained into one another. So we don't have a single encompassing framework. I would also like to mention that there is at least a third way to generate models in string theory, and this involves considering different branes in F theory. So we use different branes to probe 7 branes with constant axial dilaton. These are classified since the 90s. G gives the gauge algebra supported on the 7 brane, which from the perspective of the 4-dimensional theory, living on the D3 branes becomes a global symmetry. The delta 7 is the deficit angle in the plane transverse to the 7 brane. And from the perspective of the 4-dimensional theory, this just gives the scaling dimension of Coulomb range operators. So in particular, if we choose, if we pick one of the first 3 entries, we end up with a fractional spectrum. So this provides more examples of models with fractional Coulomb range operators. We can verify the construction by including an S-duality twist. So we are essentially combining 7 branes as the sort of quotient which describes n=3 theories, as was discussed in these two papers. This can be combined with 7 branes to get more examples of n=2 models. And we can, for instance, get the spectrum. Here, L delta 7 is supposed to be integer, but for instance, N delta 7 not necessary. So this also provides some more examples. Most of these models do not fit neither in the classless construction nor in the geometric engineering realization. Although it might be worth mentioning that at least those with L times delta 7 equal to 6 can be obtained in some way from 6 dimensions. They correspond to torus compactifications of some 1,0. Okay, so this concludes my overview of the geometric methods to construct Argyres Douglas theories. So we have seen that we can construct a large class of models. And now let's move on and discuss how we can understand some of their properties. Are there any questions? Okay, so let's go on. So let's start from the BPS spectrum. And I will focus on the method of BPS quivers, as I said at the beginning. So what does it mean? So we have to start with somehow an a priori assumption on the spectrum of the theory. So we assume that the spectrum is generated by a finite number of basic BPS states, and all others can be interpreted as bound states of those, where these numbers Ni are all positive, non-negative. Okay. And now, assuming we know the set of generators, we can define the BPS quiver as follows. So it's just an oriented graph with arrows connecting nodes. Each node corresponds to a generator, and the number of arrows between nodes is given by the Dirac paving. Okay. At first looking, it might seem that I need to know the BPS spectrum in advance in order to construct the BPS quiver. But actually, at least in the case of theories coming from geometric engineering, we have a way to directly construct the BPS quiver. Okay, so the idea is the following. If we pick an hypersurface singularity in type 2b. As we have mentioned before, we have an underlying two-dimensional theory, the Landau-Ginzburg model. So critical points of the superpotential for vacua of this two-dimensional theory correspond to vanishing free cycles in the geometry, and these are our generators of the BPS spectrum. The state is obtained by wrapping the fibrils on these free cycles. The intersection number of these free cycles gives the Dirac pairing between the states, so it provides us with the number of hours in the BPS quiver, and this corresponds to the number of solitons between the vacua of the two-dimensional theory. So we can trade the determination of the BPS quiver, determining the spectrum of the 4D theory, for the study of the spectrum of the underlying two-dimensional theory. This correspondence between 4D and 2D theories motivated this conjecture for the 2D correspondence, which in general can be stated in this way: for every n equal to theory whose spectrum can be described using a quiver, there is an underlying two-dimensional theory. In the case of geometric engineering, we can construct it explicitly. And the properties of this two-dimensional theory encodes the information about the quiver. This matrix B, called the adjacency matrix, essentially gives us the number of hours in the quiver, and this is encoded by what is called the TT star Stokes matrix, which encodes the information about the solitons of the two-dimensional theory. All these notions are discussed in an old paper by Vafa and Cotti, and we can use the technology developed in this paper to construct the quiver. Here we can give some examples. So the first one is just to consider f of this form. This is an ADE singularity. Okay. The corresponding two-dimensional model is an ADE minimal model. And in this case, using the result of this paper, one can prove that the corresponding BPS quiver is just given by the thinking diagram of type G, the finite quiver, not affine. Another example is considering a singularity of this form. This engineers SU2 super-Yamils, I've explained before. So in this case, since F is the superpotential of the two-dimensional model, the fields 1, 2, and 3 are simply massive, since they appear quadratically in the superpotential. We can integrate them out, and we are left just with the first part proportional to X4. This is known to be the mirror dual of the CVP1 sigma model in two dimensions, which is known to have two vacua and two solitons running between them. And this is the BPS quiver for SU2 super-Yamils. Okay, now, yes?
For the first case, you have the Dinkin diagram, and so every edge represents a single chiral multiplet in a specified direction. Well,
we have a single edge between the nodes, meaning that in the two-dimensional theory we have one soliton going from one vacuum to another. And okay, the Dinkin diagram becomes the BPS quiver in 4D. meaning that all the generators of the BPS spectrum have Dirac pairing, which is either 0 or 1. Okay.
But what do you do in case the node of the Dinkin diagram has valence 3? What are the directions of the arrows?
Valence 3, what you mean?
To take the
only simply laced.
Here
we have only simply laced.
Right. So take the central node of D6.
Yes.
It has valence 3. And you have 3 arrows, I guess. But what are the directions?
You mean the length of the nodes?
No. You're telling me that the BPS quiver is the Dinkin diagram. Okay. So now take an ADE quiver, which is not of type A, right? So some nodes have only one node connected to them. Some nodes have 2 and some nodes have 3.
Okay, so for instance, the central node in D type.
Yes, and for this case, I'm asking what are the directions of the arrows?
Well, I mean, this thing just means we have that state as a non-trivial pairing with 3 generators. Okay, the spectrum is given by the set of stable representations. So we have a chamber in which the only states are the generators of the spectrum, and then if we move around in the Coulomb branch, this is going to change. This is the only notion which is relevant for the spectrum in 4D.
But there could be a distinction. So if the central node will have all 3 arrows incoming, it will be different than the case where 2 of them are incoming.
Well, you know, you can perform what are called mutations on the quiver.
Yeah.
These do not change the spectrum. Okay. And if we have a simply laced Dinkin diagram, you can change the orientation of arrows as you wish.
Okay.
So yeah, it's not essential for this type of diagrams. Indeed, if you start having loops, your orientation matters, and you cannot change it arbitrarily. But for ADE, you can.
Okay.
Okay.
Thank you.
Good. Okay. So good. Now, so we have seen how to construct the quiver for the basic examples of Argyres Douglas we discussed. Then for the C2 super young mills. In principle, one might go on and look at more complicated F, although in general, it can be technically complicated to work out the set of vacua and the solitons between them. However, there are some tricks which help simplifying the derivation. For instance, if our equation F defining the hypersurface is given by the sum of 2 different F, F1 and F2, then in this case, the underlying 2-dimensional theory turns out to be just the sum of two decoupled sectors. Okay, and these end up implying that the quiver of the resulting model is a sort of product of the two basic quivers associated to F1 and F2. So I can reduce the problem to a simpler one. We can exploit this trick, for instance, to guess the BPS quiver for super Young mills with generic group corresponding F is of this type. So here we recognize the part leading associated with SU2 super Young mills, and this is an AD singularity, and the quiver is just the product. Here I just considered G equal SU6, and we also have these diagonal arrows on top. The vertical arrows give the SU2 quiver. And then we can do the same thing for G prime, and we just have the product of the two thinking diagrams. Here I chose SU3 for the vertical one and SU4 for the horizontal. So in this way, we can write down the quiver for generic GG prime. Okay.
So here you have to pick an orientation for the arrows, but this is just related by mutation to the other one. If I put the diagonals together.
So as long as you consider just one AD, yeah, the orientation can be chosen and changed at will.
Okay, so that's the same question as Amy
But
asked.
once they fit inside a more complicated structure like this, which includes non-trivial loops, then it's no longer the case. For instance, you cannot simply reverse these arrows.
Yes, but I meant also the diagonals. So the diagonals, they are...
So the set of equivalencies is given by the rules of mutations,
yeah.
which involve changing the orientation of all arrows incoming and outgoing from a node at which you mutate, and this also changes the number and orientation of these diagonal lines.
But it seems to me that this information is not sufficient to provide just the quiver. You also need to provide relations which are satisfied by the arrows, and those will be given by superpotentials.
So yeah, as long as yes, but having a superpotential requires having closed loops. Otherwise, you can simply write down gauge invariance. Okay.
Will you have at least 4 loops in the quiver that you showed below, and then there could be more?
Yeah, so in the case, in this simple case we discussed, in which you take the product of two acyclic quivers, okay, this, the right choice for the superpotential is given by including all possible terms for the shortest path. In this case, you have to include all possible cubic terms. Okay. So this gives uniformly the correct prescription for the superpotential in the special case of product of two acyclic. If you have one acyclic times a quiver which contains loops, this might change, and one has to check case by case what is the right choice. Yeah. So this complication if one goes beyond the set of examples. Yeah. In general, the superpotential is an issue.
So here there is a general question one can ask. So in the description you just gave, you could extract the superpotential from placing the problem as a tiling problem.
Mm-hmm.
Now, so the question that one can ask is, are all models by some tiling problem, or are there models where tiling is not sufficient to extract the data of the superpotential?
Yeah, in general, it's not sufficient. So if you have, for instance, products of quivers involving loops, then no. In general, it's not enough.
Mm-hmm. Okay. Yeah. So then it would be nice to give a precise characterization of those cases where it's possible. In those cases
So yeah, in this simplest case, yeah, we have a nice and uniform prescription, but in general, no, the determination, yeah, different choices of superpotential can lead to two different answers for the spectrum. Yes. So I'm not aware of a general characterization which works. This is, for instance, the case for classes theories. In general, we don't know the precise quiver for classes models precisely because of this problem. We can guess the graph, but we don't have a precise prescription for the superpotential.
I see.
Yeah, this is a limitation of the model.
Thank you.
Okay. Now, the final topic, the modular space. How can we study the X branch of this Argyres Douglas? So one possible way to attack the problem is by considering 3D mirrors or magnetic quivers. This is motivated by the following consideration. So we have seen a large class of Argyres Douglas theories come from classes. In the case of regular punctures, we know there is a general prescription to build the magnetic quiver, the 3D mirror. Even though the classes theory by itself is not Lagrangian, we always have a Lagrangian 3D mirror. This was worked out in this paper. And now we might wonder if such a prescription exists in general also for the case of irregular punctures. Well, in some cases, the result is known to be, this thing is known to be true due to mathematical results by Bolch, who studied the Itching modular space in the presence of irregular singularities and gave a quiver interpretation of the resulting modular spaces. In these two papers, a physical interpretation of the result was given with this outcome. So, at least in the case of GG prime theories of this type, we can write down a 3D mirror. This is an abelian theory which is called a complete graph. So we have n abelian nodes and bifundamentals between each possible pairs, all with multiplicity k. So this just comes from the mathematical result of Bolch. And we can actually give a physical derivation of this result using what are called the Maruyoshi-son RG flows. And this is what I would like to describe next. So the idea is the following. We pick a generic n equal to CFT, can be any, with a non-abelian global symmetry G. And then we introduce by hand a chiral multiple transforming the adjoint of G, and we couple it for a superpotential term to the G moment map of the n equal to theory. Finally, we turn on a nilpotent verb for this chiral multiplet. Let's say a principal nilpotent verb which breaks the global symmetry completely. This procedure breaks supersymmetry to n equal 1 generically, but it was observed that in some cases, for some choice of n equal to theory, supersymmetry enhances back in the IR, and the infrared fixed point is one of the Argyres Douglas theory. This method allowed, for instance, to compute the superconformal index of some of these theories. We can observe that this procedure works uniformly for all DPG theories without restriction on P and G. And the IR fixed point, as always announced, the supersymmetry, and is one of the models of type A, G. And we get all of them. Okay. Now, what I did with Sergio was to develop a tool which allows to implement this set of operations at the level of the 3D mirror. So, assuming that the mirror of the PG is known, we can determine that of the Argyres Douglas theory. So, in some cases, the DPG theory itself is Lagrangian. Here we give one example. The 3D mirror of this theory is known, and then we can apply this procedure. And in this way, we were able to derive the complete graph conjecture, like here. Okay. Apart from this class, we can proceed further with this method. Last year, we realized that actually all DP SUM theories, even though they are not Lagrangian, they do have a Lagrangian description upon dimensional reduction to 3D. They become linear unitary quivers, and the gauge group is SU or U, depending on this condition, on whether n times k over p is an integer or not. Okay. Once we have this quiver available, we can explicitly derive the 3D mirrors, as we did in this paper, for all A, G model with G of type SU. Okay. The other cases are slightly more complicated because in general, the DPG models are not Lagrangian, even in 3D. One example, for instance, is D2SO8, which is known to coincide with the E6, Milan-Nemeshansky theory. The X branch of this model is E6 instanton moduli space, for which we have no ADHM construction. And so for this reason, we do not expect a Lagrangian description of this theory independently on the dimension. However, it turns out that we can provide a semi-Lagrangian description of this model in this way. So this theory is actually equivalent to a USP4 SQCD with a symmetry gauge. This model has a monopole operator of dimension 1. So in the infrared, it has an emergent U1 symmetry. And if we gauge it, this model becomes exactly E6. So using this more involved description, we could derive the mirrors of all A, G models. The exceptional case is still work in progress, should appear soon in this paper. And a nice special case is this one. Here, H is the dual Coxeter number of G. In this case, the 3D mirror has a nice description. So it's an abelian theory with gauge group U1 to the power the rank of G. So we can think of this as the Hartan of G. And the matter fields are given by a collection of hypermultiplets, which are in one-to-one correspondence with the positive roots of the Lie algebra G. And the charge of these hypermultiplets is given by the components of the corresponding root vectors. So in the case of SUN, each root is charged under only 2 U1s. So this produces the complete graph we saw before. And for general G, we have a more complicated result. In particular, for G exceptional, we don't even get a quiver because several hypermultiplets are charged under multiple U1, so regardless of the basis you choose. Still, we do have a Lagrangian description for this 3DC or last thing I would like to mention is that generically this abelian theory is accompanied.
Sorry, quick question.
Yes.
You say it's not a quiver because these are not bifundamental?
Yeah, they are not by
Okay.
If you have a hypermultiple
Some polarized quiver.
for nodes, so yeah, you can write down the matrix of choice, but you don't have a graph.
Okay.
So in general, we have to go beyond the quivers.
Yeah, I see. Okay. Thanks.
Okay. Last thing I would like to mention is that generically, our gauge theory is accompanied by a 3 sector, and this signals the presence of non-mixable sectors in the 4-dimensional field. So in favorable circumstances, at the generic point of the X branch, the low energy theory is just given by a collection of hypermultiples. But in general, it can happen that the low energy theory includes a strongly coupled non-trivial sector, which has no X branch and therefore is not Xable. And upon dimensional reduction, this non-Xable part becomes a collection of 3 twisted hypermultiplets. So this seems to indicate that this property is true in general. Every time we have a theory without a X branch in 4D, this can be strongly coupled, non-trivial, but upon dimensional reduction, it becomes equivalent to a 3 theory in 3 dimension. Okay, so let's summarize what we have seen. So we have several tools to construct strongly coupled CFTs, also with non-integral spectrum. We have several geometric methods which are partially overlapping. It's not clear how systematic our current understanding of these theories is. And the natural question is whether we can find a unified framework in which all these models can fit. And then we have several efficient techniques to study the properties of these theories. In particular, a lot of effort has been done in understanding the spectrum and the moduli space of these theories. We have seen that for many Argyres Douglas theories, we can find Lagrangian 3D mirrors. An open question is whether we can find a systematic method to construct the 3D theory. A possible issue is that some Argyres Douglas theories, upon dimensional reduction, become gauge theories in 3D, which are bad. So it's not clear in this case what the 3D mirror is. Maybe there are some issues. It's not clear how this fits with this program in general. But yeah, it would be interesting to understand how far we can push this method of 3D mirrors to encode the X branch of these models. Okay, thank you for your attention.
All right, let's thank Simone. Do we have questions? So maybe I can start with a question now, which is a bit more general, not specific. So there are all of these different constructions of Argyres Douglas theory that you mentioned. And do we have examples of Argyres Douglas theory which don't fit in any of these? Or so my question more
something which doesn't come from geometry, you mean?
So how many Argyres Douglas so in the set of Argyres Douglas theories, how big of a patch are we exploring when we're using these GG prime or the DPG theories and all of this?
Well, yeah, that's precisely the thing which is not too clear at the moment. So, okay. one way to try to address this point could be push more the original method. You just start with a gauge theory and you try searching for new exotic theories. For instance, the case of G2 SQCD was addressed just last year, 25 years after the first examples, and it was done by using a different method, not exploiting the curve. So, okay, this has only been partially addressed, so this might reveal some surprises. The model found in the case of G2 of G2 SQCD as a class S realization involving twisted panel.
I see.
So it's a little bit elaborate, but we can find one. I'm not sure if what we know already covers everything. I'm skeptical about it.
So this is the paper by Justin and Mario?
Yeah, Justin and Mario.
Mm-hmm. Okay, I see.
Now, classification, yeah, should require having probably a better insight about higher rank theories, which at the moment is still a bit hard.
Okay.
Now, let's say everything up to rank 2 fits in at least one geometric construction. So,
yeah. Of course, it's hard to talk about theories which we don't know how to construct. So,
yeah, the point of this is that okay, the embedding inside Lagrangians is one alternative way, but yeah, it's hard to construct directly strongly coupled theory.
Yeah, sure.
Without appealing to a geometric method. Another thing might be worth mentioning is that last year, Denxier proposed a method to rederive our results about 3D mirrors. So he was considering classes theories, but introduced an auxiliary Riemann surface with a different set of auxiliary punctures. And from this, it was possible to design a combinatorial prescription which produces the quiver. So it's not clear at all where this description comes from. Looked a bit ad hoc just to reproduce the results he expected. But maybe this suggests the possibility that there is another way to describe these models, apart from the 3 methods I have already described, although I'm not sure.
And then I have, well, maybe someone else wants to ask, but okay, I'll just go. I have another question for the very last point you mentioned, the bad theories. So are these the type of bad theories where you still have a notion of the Higgs branch? So you can still analyze the Higgs branch as one single entity, or are these the type of bad theories where you get several distinct components in the Higgs branch which are somehow separated along the Coulomb branch and it gets more tricky?
Well, the examples I know usually involve SU groups. Okay, typically are D or E-shaped quivers. So yeah, I'm not sure. It's a bit complicated to answer. They are not linear quivers, and they involve both SU and U groups.
Okay. So then there is the possibility that you have multiple cones. This is
the presence of SU might imply multiple cones. Yes.
Yeah. Okay. So then it really gets quite then it gets complicated indeed. Okay. I'm
not sure. It might be that this theory is a special feature, but at the end, the problem is not so untractable. They don't have a classification at the moment of such cases. For sure, one thing I can say is that upon dimensional reduction, one can get unitary quivers with exceptional shape. And so probably the general case requires also extending the mirror map to this set of models.
Mm-hmm. Okay, do we have more questions for Simone? Well, I guess that you really were extremely clear. So
yeah,
no one is left
question, but
confused.
I want to say it was extremely clear, and it was very, very nice review.
Thank you. Okay.
Right. So then I'd say let's cut the recording. Let's give Simone one more round of applause.
Simone,